Hello and welcome to episode number 15 of CS350 Online. I'm your host as always, Leslie Eston, and in today's episode we are going to continue our discussion of virtual memory. And with that, we are going to actually hopefully finish our discussion of virtual memory by talking about one of my personal favorite topics, which is on-demand paging. And no worries here, I'm just going to adjust the green screen for you. So, for those of you who are watching live, first off, I apologize for the late start. As many of you have noticed over the last couple weeks, we've had quite a few issues with the live stream where there's been audio-video sync issues, and it's been just overheating issues and all of these lovely things. And today, I'm actually live streaming from a brand new machine. So it took a little bit of extra time to get it set up. Now, we did do a test run over the weekend. Some of you might have noticed that the Twitch stream actually became live for very short periods of time. And that's because I wanted to make sure that the stream was actually functioning. And indeed it was. But as with any new machine, there's always lots of little hiccups and things. So we're actually streaming today, by the way, from a desktop computer, and so we are not streaming from Mac OS anymore and a laptop. We are streaming from a beautiful Ryzen 9 5950X with 128 gigs of RAM and an RTX 2080. So we shouldn't have any issues. But if you are watching live and you do notice some issues with audio or video, please do let me know so we can make some adjustments. It actually took a little bit of time to, of course, port all the whole setup from macOS over to Linux, because that's what we're using now. So there's always going to be bits of hiccups when you switch over to a new machine. So do let me know. All right, but if you're following along with the textbook, of course you want to be looking at the paging section. And then, for those of you who are working on assignment 2, please make sure you read over that common error post because it's got a lot of information about a lot of the common errors. And as I see more Piazza posts about certain errors that I have forgotten, I will add them to the common error post. That way you can search that first. Of course, now let us talk about the OS of the day. Now, I'm going to make this just a wee bit smaller. See, one of the other changes is usually what happens is I'm actually using two screens. My Mac's screen would normally be the one that I'm streaming, and then on my other big screen I have, you know, all the software I use to do this. And now I just have the one screen, so it's going to be a little bit weird for me. And when this, if you're wondering what are these this funny chart down here at the bottom, this is actually a called P sensor, and this is a temperature monitor, and I just like to keep an eye on how this machine does with the streaming operation. I don't suspect that it'll have an issue, of course, because it's a water-cooled system, but it's always good to keep an eye on that. So you can watch along as my CPU chugs along. All right, the OS of the day today is one that some of you might have actually heard of. It's called QNX, and so QNX was actually released in 1982, and it's from a group called Quantum Software Systems, which is now owned by BlackBerry /RIM/ whatever you want to call it. I'm always going to call it RIM because they were always RIM to me. This is an interesting operating system because it actually originated from our own university. And what apparently happened, or so the story goes, there were two students who were taking trains. I don't know what the course number is for trains. It's the real-time operating systems course in 4th year, you know, one of the big 3. And for some reason that just didn't give them enough to do. So they thought to themselves, you know, the world needs a real-time operating system, you know, not just a toy. So they went out and they actually developed QNX. And it's a Unix-like operating system, but it has a microkernel instead of a monolithic kernel. And for those of you who don't remember microkernel, it means that they put the absolute bare minimum of functionality into the kernel. So in fact, their microkernel, which is only 44 kilobytes, it's very, very tiny, has interrupt redirection. You'll note I didn't say interrupt handling, I said redirection. It has the timers, the CPU scheduler, and inter-process communication, and everything else, including their implementation of virtual memory, is a user process that actually uses the message passing via the inter-process communication to actually do its jobs. So that's kind of an interesting thing. And by being real-time, remember that that is putting a stricter bound or guarantee on how long it takes for the operating system to respond to certain events. So things like the lock suddenly becomes available, and the thread that was woken will actually be able to get the lock much faster or with a guarantee, unlike our own operating system we're working on. Another thing is, because this was a microkernel operating system with such a tiny, tiny kernel, one of the places where you actually see QNX a lot is in embedded operating systems. And for those of you who are not familiar with that particular term, it means that the OS is actually on a chip. So instead of it being on like a disk that loads when you boot the computer, it's actually embedded right on one of the chips on like a board. And that's going to give you a lot of performance boosts and things like that. Not as much flexibility, but it does give you some extra speed. Now, where is this operating system used? So, I mean, originally it was used by the Ontario School Board, because a lot of Canadian companies and Canadian parts of the government have these rules, you know, a certain percentage of content must come from a Canadian source. And actually, maybe you don't know this, but if you have like a Canadian radio station or a Canadian television station, there's actually some kind of law that states that a certain percentage of the content has to be of Canadian origin. Interesting story. And where QNX tends to be used today is things like industrial applications, so in the automotive industry. At the time I wrote these slides, which was quite a few years ago, there were over 56 million cars that were actually running a QNX operating system, and you usually see it as part of the navigation system. So you know how some computers have like the little computer screenies? A lot of them are actually running QNX. You'll see the same thing on in airplanes where they've got the little seat back things. QNX is a popular OS there. Something called a carrier grade router. That means, you know, the big routers that like Rogers would have. And of course, if you have a Playbook or a BlackBerry, it's also running QNX, but I'm not sure anybody has those anymore. All right. So, those of you watching my temperatures, it looks like they are running cool as a cucumber, 44 degrees Celsius. Which is, by the way, like 20 degrees cooler than my laptop sitting beside this desktop is running right now. All right. So where did we leave off last day? So, switch over here to these other lovely slides. So I know it was 5 days ago, so you may not remember everything we were talking about. We left off, we had been talking about paging. And one of the side effects of paging was that translation no longer was as efficient as it had been with segmentation or dynamic relocation. And the problem there wasn't actually that the calculation was inefficient. The problem was more that when we want to find the frame number for this page, the number of memory lookups we would have to do was dependent on the height of our multi-level paging. So, for example, in the computer sitting in front of you right now, we use 4-level trees. And that means that for every lookup, we actually have to go from the MMU to RAM 4 times, which is a really costly operation, just to retrieve our frame number. So we talked about in our last episode how we were using a special cache called the TLB, or Translation Look-Aside Buffer, as a means of reducing the amount of time it takes to actually get that frame number. And the whole idea behind the TLB is that it's this wee organized, tiny organized cache sitting on the chip, and it is going to store a bunch of page table entries. And then what happens is when your MMU is given a virtual address to translate, it's going to look for the page number in the TLB, and if there's a hit, then it never had to leave the chip in order to actually perform the translation. So we get the frame number, it's a TLB hit, we move on. If, however, the page number is not found in the TLB, then what we end up having to do is either getting the hardware to perform the task of going and getting the frame number, so actually traversing the tree and getting the final frame number, or we're going to ask the operating system to solve the problem for us. So a hardware managed TLB would be when the hardware actually goes out to the page table, finds the frame number, and then updates the TLB. And a software managed TLB was when we have a TLB miss, we throw an exception, and the kernel of the operating system is going to find the entry and update the TLB for us. There's advantages and disadvantages to each approach. Advantages of the hardware approach are it's going to be faster because we don't have to throw an exception and do all that saving of the trap frame and then figuring out what kind of exception it is and then finally calling VM fault to solve the problem for us. So it's much faster, but the downside of the hardware managed TLB is that the hardware, the architecture, is now going to be dictating the format of the page table to the operating system. And we may not want that. We may want a lot more flexibility. The software managed TLB is a little bit slower because we are involving, exceptions and that whole, with the processes and the system calls, you saw all the different calls that we had to make just to solve the problem. So it is going to be slower, but the advantage is the kernel doesn't have to use the exact form of a page table entry that the hardware might be dictating. So we have a lot more flexibility in our implementation. Another thing is that to remember is that the TLB has a fixed number of entries, and for OS 161, our TLB can only actually fit 64 entries. And the problem that we run up against is at some point your TLB is going to be full. And so you actually need to evict somebody that's already there and so that you can put the new entry in. And there's lots of different cache eviction strategies that you can use. You could use the oldest one. You could choose the least recently used one. You could pick a random one, which actually works surprisingly well, all things considered. There's lots of different ways that you can choose to evict. And again, a downside of the hardware method is that that is going to be decided by the hardware. Whatever cache eviction strategy the hardware wants to use, that's what you're stuck with. Whereas with the software managed TLB, you can do whatever you want. So if you want to implement some kind of complex cache eviction strategy, you go right ahead and do that. But all right, and for the record, if you're looking at, well, which cache eviction strategy does OS 161 use? It doesn't use any. When the TLB is full in OS 161, it kernel panics and dies. But good news, you're going to fix it in assignment 3, right? And if that scares you, don't worry. You're going to be calling an already implemented cache eviction strategy and then just integrating that into VM faults. You don't actually have to implement the strategy yourself. All right. So the other thing I wanted to remind you of before we move on to today's topics are just the format of the Mips TLB. And that was that the TLB entries in our Mips architecture are actually 64-bit, so they're 2 words. And there's this 6-bit field here that we don't use that would store typically the PID of the process that this page table entry belongs to. Again, I mentioned this before, it's not used. And this is actually a field on TLB entries across most architectures, and up until very recently, this field has also been not used. But in the last 5 or 6 years, and I'm not even sure it's been that long, we've actually, on Intel and AMD architectures, they've actually started using the PID field. And one of the reasons why you want to do this is when you have a context switch going from a thread from process A to a thread from process B, you actually need to clear the TLB because all of those page table entries only correspond to the process that's currently running. And so when you do that context switch, you would get TLB hits for stuff that for things that aren't in your address space. So you'd be doing garbage translations, and we don't want that to happen, obviously. So you either have to clear the TLB on a context switch, or you have to use this PID field. And this is what we've been using lately because it gives you some added security, but it also gives us the ability to have this thing called cache affinity, which is between the time that you were originally running and then the time that you actually get to run again. There's a probability that some of those things you left in the cache will still be there, which we want. Because if they're still in the cache, then we don't have to reload the cache from scratch, which is nice, I think. All right. But we don't use that field right now in Mips. It's just modern architectures are starting to use that. I'm gonna make sure I'm scrolling the wrong direction. I've been using a Mac for so many years, and I haven't actually used a desktop Linux environment in a long, long time. It's nice. It's very refreshing to actually be using something that works. Oh, that's interesting. Apparently, I opened the wrong slides. Okay. So, the last thing we talked about in our previous episode was just how OS 161's virtual memory works. Remember that it is using segmentation, even though our MMU uses paging. So, in particular, how we're making that work is that even though virtual and physical memory are paged, so they're logically divided, the segments of the address space have actually been contiguously allocated. And we just keep track of, in our address space structure, the start base virtual address and the start base physical address and how many pages it is. And then using that information, we don't need a page table because we know that if you are in this address range, you are a part of this segment, and here's how you translate, and it's very trivial to figure out what the page to frame mapping should be for that. Of course, the downside of this is that we have external fragmentation problems. Oops. The address translation, again, we are not using a segment number explicitly. What we're doing is we're computing for each of the 3 segments. We're calculating the low and the high address, and then we're asking, is the address that has thrown the fault between that range? And if it is, we compute the physical address, and then later on in dumb-VM, we'll actually translate that to a page number. And of course, if you're not in the code segment, and you're not in the data segment, and you're not in the stack segment, then you are not in this address space, and therefore we throw a fault. We did some address translations as well, and I'm not going to go over that again. And we also talked about where that address space structure actually came from, and that was the ELF binaries. And no, I do not have OS 161 working on this Linux distro just yet. I have not had a chance to do that. That takes a little bit of effort because I'm using like GCC 10 over here, and that means I need to actually do some patching and some manual editing. But no worries, we'll get that working. All right, so there's a question on Twitch, and the question is, why didn't older architectures use the PID field? So I'm not 100%, I can't answer that question because I've not been involved with chip development. My understanding, though, is a lot of chips actually didn't keep track of the PID of the current process, and so that was just information that they didn't even have access to. Whereas a lot of the modern chips are now actually keeping track of a unique identifier for each process, so they can actually do that. But it's possible that the MMU developers were a bit ahead of their time, and so they put that field in there knowing that this would be useful, but maybe we don't have support for this just yet. The other thing is there was probably a question of, is there really a benefit to this? And, you know, it's argued, like, I feel like, yes, there should be a benefit in terms of cache affinity and making sure that, you know, you get some of that benefit, but what really I think pushed people over the edge into actually using that wasn't actually the potential for cache affinity. I think it actually came down to security, where you're not going to let a process perform a translation using a page table entry from somebody else. So I think it was more of a security issue that actually forced the issue. And I think the switch actually happened right around the time of Meltdown Inspector. But don't quote me on that because I'm not 100% certain. All right. So what I want to, new topic today in OS 161. I want to talk about virtual memory for the kernel. So right now, everything that we've talked about has been virtual memory for the user program. We've never actually talked about what kind of memory OS 161 or its kernel or the operating system kernel in general actually runs in. Like, does it use virtual memory or does it use physical memory? And if you think about it, you probably want it to use virtual memory, because if you let it use physical memory, then you can find it and you can start actually, you know, picking it apart and trying to find data you're not supposed to get into. So realistically, we do want the kernel to live in virtual memory, but that poses a really interesting problem. And that interesting problem is, if the kernel is implementing virtual memory and the kernel is supposed to run in virtual memory, then how does that work when the kernel's booting up? That's called the bootstrapping problem. The bootstrapping problem is actually tends to be architecture specific. And usually what happens is it's the architecture that's going to dictate to you how the kernel's virtual memory will work. And in OS 161, we'll show you how the kernel's virtual memory works in a minute, but it's very simple and it's very much dynamic relocation. But it's fine, right? Works pretty well. The other problem you have is this sharing problem. So we often have this job where we need to take data from one of the address spaces of the user program, and we need to take it and we need to put it into the kernel so that we can put it into another address space, or so the kernel can use it. But if the user program and the kernel are using the same address range, then how do we differentiate the addresses as being, I'm trying to pull from address dead beef in the user program and put it into address dead beef in the kernel? How do you do that? So there's a sharing problem. Sharing problem is actually very easily solved, and we'll finally explain to you why your stack actually lives in the middle of the virtual address range instead of the end, as 136 has taught you. And the reason is, when we solve the sharing problem, we took our range of virtual addresses and we divided it into two. Now, the split isn't always a 50-50 split, but it is certainly the most common split. And you can easily write a program on your operating system to see that you have a 50-50 split. It's simply put some stuff on the stack, and you'll see that the stack lives roughly at the 50% mark. So it doesn't have to be a 50-50 split, but all the operating systems that you are using a 50-50 split. So Mac OS X is using a 50-50 split. The Linux kernel uses a 50-50 split. Now, that's not necessarily a requirement. That's just the default. And Windows also uses a 50-50 split. You could use a 25-75 split or a 60-40 split. You can use whatever split you want, but 50-50 is the most common. And the idea is the lower 50%, or the lower half of your addresses, are going to be for the user's address space. And that is why the stack lives in the middle of the virtual address range. It's because the middle of the virtual address range in a 50-50 split is the end of the address range that the user program is allowed to use. So that is why your stack lives in the middle. And then the upper 50%, or the upper half of the addresses, are reserved for the kernel. Now, what this does is it makes it look like the kernel is a part of every user address space. And there's not multiple copies of the kernel. There's only one copy of the kernel. But because it uses an address range that is unique for all processes, it makes it look like the kernel lives in every address space when it doesn't. So Now that you have split this into a user range and a kernel range of addresses, the fun thing is we can now differentiate between which address is a user one and which address is a kernel one. So copying from the user into the kernel now becomes very easy. And if you've been on Piazza there, you'll note that, let me just open it up here. Piazza. If we go into common OS 161 errors, oh, see, yeah, this is funny. So I open up Chrome, and my temperatures go from 44 to 56. That's amusing. No worries, no worries. This computer isn't going to blink over a temperature like that. So if you go into here, you'll notice that I have outlined the different kinds of memory errors that you can see. So if you see the program counter as less than this address here, that means it's from the user program. And if you see a program counter or EPC that is greater than or equal to this address here, that means the error occurred in the kernel. You can also use this to determine whether you had a problem with a kernel address trying to be used in the user program and so on and so forth. Where did I get this designation of these addresses are user and these addresses are kernel? Well, quite simple. I got it from this 50-50 split here, which OS 161 uses. So that is how I know where your memory problems are originating from, is based on what is the program counter and what is the virtual fault address. So for example, if you have a fault address that is below in the user range and you have so your EPC is in the user range but your fault address is in the kernel range, then I know that you accidentally wrote a kernel address to the stack of the user program, and that would be really bad, which is obviously why it threw a fault. So that is how we're actually able to tell what's going on, is based on the fact that the virtual addresses for the user program are different from the virtual addresses for the kernel. So that's how we solve the sharing problem. All right. Now, OS 161's virtual memory is kind of funny. So you know that for the virtual address range, for the user program is the lower 50%, so from 0 to 7FFFFFFF inclusive. And we know that this memory here, in this lower 50%, is paged, just like our physical memory is also paged, even though we are technically doing segmentation. We still have the ability to do paging. And this memory will also make use of the TLB. But how is the kernel's memory, the kernel's part of this address range, actually organized? Well, it's organized quite simply. It is actually subdivided into 3 different segments. There's KSEG 0, KSEG 1, and KSEG 2. Now, it's very easy to believe, looking at these 3 segments, that you've got a code segment, a data segment, and a stack segment that's awful big. But actually, that's not what these are at all. So KSEG 0 is actually the memory that is available to the kernel itself. That's where the kernel's data structures live. It's where the kernel code lived. It's where all the kernel stacks live. It lives in KSEG 0. And there's 512 megabytes allowed for that particular segment. And if you're sitting there thinking to yourself, oh my goodness, what if my kernel needs more memory than that? This is a 32-bit address space. This chip is about 20 years old. I'm not sure how old the Mips R3000 is. Let's look it up. Advantage of having now 3 computers on your desk is that you have all this power to look up things. So let's see. So the Mips R3000 was introduced in 1988. So I don't think we were too worried about operating systems kernels being bigger than 512 megabytes, because in 1988, the consumer operating systems that we had were DOS and like Windows 2 and an older version of Mac OS. And believe me, so Windows 3.1, which is like the really late 80s, early 90s, that was only like 5 megabytes to install. So this is plenty of space. You're thinking of today's operating systems, which have access to significantly more space. And, you know, if you're trying to do like an install of like Windows is like 5 gigs, we're not talking about that. We're talking about operating systems from the late 80s, early 90s, and none of them were that big. And so 512 megabytes for your kernel's address space was way more than we could ever use. No one would do that. All right. So that's KSEG 0. KSEG 1 is an interesting thing, and it's not going to make a lot of sense today, but when we talk about devices in 2 or 3 episodes, you will actually come to understand KSEG 1 a lot better. KSEG 1 is set aside for talking to devices. So they are special address space. It's a special address range. And whenever the kernel sees an address in that range, it knows you're trying to talk to a piece of hardware. Now, there's 512 megabytes associated with this particular segment, and I can tell you we don't even come close to using all of that. Not even close, because we don't have that many devices. We just don't. Even on the computer I'm sitting in front of today, there's not that many devices. I mean, okay, fair. The RTX 2080, that's a pretty big device. But like other than that, I have a keyboard plugged in. I have a mouse plugged in. I have a microphone and a camera plugged in. None of these things need a lot. Okay, admittedly, the camera does, but anyways. Not in the 80s. All right. Now, what about KSEG 2? It's not used. It's unused. So that is not OS 161 dictating that. That's actually Mips. So Mips does not use the final gigabyte. You can't use it. If you find an address in that range, you're probably going to get a bus error, which means there's an invalid address on the bus. Now let's look at this in a little greater detail. So we know that the memory for the user program is paged. So technically we would use page tables in the TLB to actually perform those translations. But what about the kernel? So the kernel's memory is not paged. It's going to use dynamic relocation effectively for its translation, and that's actually dictated by the hardware. So we know that the first segment, KSEG 0, actually maps to the first 512 megabytes of the address space, or of physical memory. So to translate from a KSEG 0 address, virtual address, to a physical address, you subtract the start address of KSEG 0 in virtual memory, which is this 80000000. Now, does this mean that the user program cannot use any of the pages contained in the first 512 megabytes? No. Remember that we aren't actually using all of KSEG 0. It's just how much space we've permitted the kernel to use for this segment, but in reality, it probably only uses a few megabytes of this space. And so any of the pages that we are not using that would correspond to the first 512 megabytes of physical space could still technically be used by the page-to-frame mappings for the user address space. So they can actually overlap. Okay, that's not so bad. Now what's going to happen is when the MMU, if the MMU sees that the CPU is in user privilege, then the MMU will only perform user address translations, which is the page-to-frame mappings. If, however, your CPU is in privileged mode, then your MMU can translate the kernel addresses if it sees them. So if it sees a kernel address that is something in KSEG 0, it will use this address scheme of simply subtracting this address here to do it. That's not so bad, right? Very easy translation. What about KSEG 1? This is where things get very weird. So Kseg1 also maps to the first 512 megabytes of physical memory. So to perform an address translation, you simply are going to subtract the start of Kseg1 in virtual memory to get the physical address. So you subtract A0000000 from the virtual address. Okay, but now you're telling me that Kseg0 and Kseg1 overlap in physical memory, and that's not possible because they'd be overwriting each other. At least that's what it looks like, except that's not how it actually works. So what you don't know is that there are very few addresses in Kseg1 that we actually use, and they typically are at the very end of Kseg1, so at the very back of Kseg1. And I already told you that even though we have 512 megabytes technically for Kseg0, we wouldn't come up against that. There is no operating system that I know of that was run on this chip that would ever even come close to using all that space. So what actually happens is because we only use a tiny part of the back of Kseg1, and we would never use that in Kseg0, even though they technically completely overlap, the used portion of Kseg1 would correspond to a portion of Kseg0 that we wouldn't actually be using. So there's no real overlap. Does that put a restriction on the operating system? Yes, obviously it does, but it wasn't considered an issue because the operating systems were so small. Again, this chip was released in 1988. You're not looking at operating systems that were very large. Like I had DOS, and DOS was a single 5¼ inch floppy, which stores 365 kilobytes of data. And when I was installing Windows 3.1 in the early mid-90s, like before 95, you were looking at 4 disks to install Windows 3.1. And you're thinking CDs. No, nobody had a CD drive back then. Nobody could afford that. I'm talking 3.5 inch floppies, and each 3.5 inch floppy is 1.44 megabytes. So you've got 4 of those, that's like 6 megs installed. So you're looking at really tiny operating system footprints back then, which is why it was safe to have these two things overlap, is because we knew we would never use all of Kseg0, so having that address range overlap was okay. Now, Kseg0 and Kseg1, again, you can only actually perform these address translations when you are not in user privilege mode. So if you have to be in privilege mode for the MMU to actually perform these, because otherwise it'll throw an exception. It's an invalid address. Now, how do we deal with Kseg2? You don't. You don't deal with Kseg2 because Kseg2 is invalid. So if you get a Kseg2 address, exception, bus error. So the question on Twitch is, what would happen if we did use all of Kseg0 and Kseg1? Well, it wouldn't work because you'd actually have 2 regions overlapping themselves in physical memory, so it would just be garbage. It just couldn't work. So this only works because we know that the operating system isn't going to use all of Kseg0, and so we'll align it all at the beginning, and we know that Kseg1 is all at the end, and so we know that this is just going to work out. And the operating system, of course, is going to know what region of Kseg1 is in use, so it will know not to use that region of memory. But again, for this particular chip, that's not going to happen. It's just not. Yeah. We're not going to run a giant operating system on this chip. That would be crazy. All right. So there is a little sample problem that you might want to try, and it is on. See, I don't actually have everything set up yet because this computer arrived on Friday, and, installing Linux when you have to deal with the UEFI BIOS stuff is such a pain. So I've been trying to get this up and running as quickly as possible, but we're still a little bit behind in getting that done. So if you're in the handouts, which we've put on Piazza, there is a Mips Translate. Let's bring that over here. And what it's got is it's got a page table, and it's got a bunch of physical addresses. And what this is asking you is, given this physical address, what are all of the possible virtual addresses that could translate to this physical address? Not which one is actually using it. I want to know what all of the possibilities are. So the hint I'm going to give you is for each of these addresses, there is at least 2 possible virtual addresses that could translate to these physical ones. So I'll let you try this, and if you want to post this on Piazza to let me, and I can check over the answers, you're welcome to do that. Again, this is Mips Translate, where translate is spelled with an X. Weird short form. All right. So the last thing I want to talk about in virtual memory is this idea of exploiting secondary storage, also known as, I dropped something, also known as on-demand paging. This is so fun. So I have 3 machines here, and they all have Bluetooth enabled. And when I turn my tablet on, so my pen entry system, it's a question of which of the 3 computers will pair with it first. Let me just tell you, the desktop wins every time. Which is nice. It's nice, because normally I have to actually get Mac OS. I have to manually tell it to pair with the device. I always struggle to get it to pair with it. Whereas Linux seems to be able to do it instantaneously. It's great. It's nice to have something that actually works. All right. So here's the problem that we want to solve. Sometimes we are running more programs than technically we have physical memory to support. Let's actually see what this machine's doing. Oh goodness, I can't even read the text. It's so tiny. I have got to update my bash RC file. Okay, so here we are. We've got a terminal open. I'm going to run top, and it's going to look all pretty and nice because it's real top. And I can tell just by looking at this that, you know, I have 128 gigs of RAM in this machine. And I know right now I'm not using all of it. It looks like I'm using about 6.5 gigs of that. But I don't have much open. So I've got OBS streaming at 4K. And I've got, you know, the camera dumping into that and things like that. But that on this machine is nothing. So I'm not even coming close to using all the RAM on this machine. So we don't have any problems here. But if I were to open up a bunch more tools, technically speaking, I don't have any more tools installed right now. But supposing I had something like DaVinci Resolve, supposing I had MATLAB, supposing I open up 50 tabs in Chrome, it's conceivable that at some point I'm going to have more programs running whose total address space requirements would outweigh what actual physical memory I have. It's going to take a lot more effort to do that on this machine than on the Mac. The Mac, it's effortless to do that, but not this one. Yay for RAM. Well, how does that work? How can you have more programs open than you technically have RAM for? Well, it's easy. You just don't store all their address spaces in RAM. You do make use of secondary storage. So the idea is, if you want to have lots and lots of processes running, let's just keep the parts of the address space that they're not using stored on your disk, because you're not using it right now. And only keep the region of the address space you're actively using right now in memory. And that is going to let us run way more things than we can technically fit into memory at once. Another thing it lets us do, this idea of keeping only the active region of the address space in memory, is it's going to let us actually have virtual address spaces that are larger than the amount of memory that we have. And I may be thinking, how does that even happen? Well, so I do, as I mentioned in the first episode, my research area deals with a lot of film production. And I can tell you that it is very common for me to encounter images or shots of film that are gigabytes in size. So I have images. There was a documentary I worked on back in 2014, and each image that I worked on was something like 5 gigabytes in size. Each individual image. And I had to take those images and I had to actually decompose the image into layers by depth. So you're taking this huge image that Photoshop was like, I'm not even going to try to open this. And you've got to divide it into like 128. And I actually think it was 256 layers that I had. So you've got this huge memory footprint, like absolutely enormous. Way bigger, and the computer I did it on, I think had 8 gigs of RAM. I don't know. I don't remember. It was like 2014. So how did that work? Well, it worked because it was storing parts of the address space on my disk instead of storing it all in RAM. So how does that actually work? So I'm going to get out of Top. Top, by the way, actually uses a surprising amount of processes. And see, OPS here is using 232% of my CPU. This is a 16-core CPU. We can run 32 threads at once. It's nothing. Probably seems silly, but it's exciting to actually have a machine that doesn't overheat and die doing basic things. All right. How are we going to do this? Well, we need to keep, number one, we need to use paging. I mean, it's not that you couldn't massage segmentation into doing this, but it wouldn't be as effective. You really need to do this with paging, because that way you can only keep very small pieces of the address space loaded instead of bigger contiguous regions. So what we need to do is we need to keep track of all of the pages that are actually loaded into RAM right now and ones that aren't. So we're going to add some stuff to the page table entry. What we're going to add to the page table entry is a bit called the present bit. If the present bit is 1, it means that this page table entry and the page that it corresponds to is actually sitting in physical memory right now. So when I get a page table entry, I first look at the valid bit. If the valid bit is 1, then I know it's a valid address. And I should proceed with trying to perform the translation. The next bit I look at is the present bit. If the present bit is 1, then not only is the page valid, but it's also in memory, so proceed on your way to doing the translation. If, however, the present bit is 0, that means, yes, you have a valid page, but this page hasn't actually loaded into memory right now, so we can't perform the translation until you load this page into memory. This is also the situation where you encounter a page fault. There's a TLB miss because you should not have anything in your TLB whose present bit is 0, because that doesn't make sense. If the present bit is 0, you don't have a frame number because you are not in RAM. So why are you in the TLB? So the TLB should not contain anything with the present bit of 0. So you're going to detect these page faults through TLB misses, and then when the operating system kernel handles the TLB miss, it's going to see that the present bit is 0, meaning that the TLB miss was actually caused by a page fault. And then on the page fault, we'll have to find a free frame of physical memory to load the page into, then we update the page table, we update the TLB, and then the address translation can actually happen. Okay. And then we call the set of all pages who have the present bit set to 1 for a process that's called the resident set. That is what is living in memory right now. And this makes a lot of sense if you really think about this. Because if you look at a program like MATLAB, which has got all this crazy stuff that most people didn't even know existed, like the ability for MATLAB to take MATLAB code and spit out a C program, which it can do, by the way, that is equivalent to the MATLAB program. You connect, like, most people don't even know it can do that. So if I'm sitting there multiplying two matrices, why do I care about the ability to dump this MATLAB code into C? I don't. So why have that in my address space right now? Why have that loaded into physical memory? That doesn't make sense. And it's just like right now on this machine, I'm using a standard QWERTY keyboard. So why would I let a Dvorak keyboard driver be polluting my physical address space? That doesn't make sense. I don't want it in RAM because I'm not using it right now. So this is a really great way to make sure the only parts of the address space that are in memory are the parts you're actively using right now. Now, probably sounds really cool, but it's not perfect. So I've already talked about this slide, so we're going to skip it. We're going to go on to slide 51. And here's the problem. So OS 161 does address space preloading, which means it loads the entire address space into RAM when the program is loaded. There are advantages and disadvantages to both approaches. The advantages to preloading the address space is performance. You always know all of the time that every page of the address space you could ever access is there in physical memory waiting for you. Fast. Very, very fast. The downside, of course, is that it's going to restrict the size of the process you can load, and it's going to restrict the number of processes that you can have running at the same time. The advantage, of course, of on-demand paging is you have taken away the restrictions for the size of the address space. You've taken away the restrictions for how many processes you can have. I mean, there's still restrictions, but on-demand paging is going to let you support millions more. Okay, not millions, but a lot more processes than what address space preloading would ever let you support. The downside is anything that you want to access that isn't in RAM is on disk. And disk access is orders of magnitude slower than RAM. And if you're sitting there, yeah, but I've got like an M2 disk. Yeah, it's still slower. It's still orders of magnitude slower than RAM. So just to give you a picture here, we've done a little bit of math. So let's assume that secondary storage is 1,000 times slower than memory access, especially if you have a mechanical disk, like with actual spinning parts in it. This is definitely going to be true. Let's look at the cost of page faults per operations. So if 1 in 10 instructions requires, 1 in 10 memory access is a page fault, then your program using on-demand paging is going to be 100 times slower. What? So instead of a minute, it takes 100 minutes? I would check it out the window. 1 in 100, 10 times slower. So I go from 1 minute to 10 minutes, still going to check it out the window. 1 in 1,000 operations causes a page fault, it's twice as slow. So you can see here that the frequency of page faults is really going to impact the performance of our program, because a page fault is going to mean that we have to get the data from disk instead of RAM. So how do you deal with these page faults? Because they're obviously very problematic. Well, you could restrict the number of processes. So nobody ever has to go to disk. I don't want to do that. I really don't want to do that. I don't want somebody telling me I can only have 10 Chrome tabs open. Like, looking at my other computer here, let's see, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have 20 Chrome tabs open. And I mean, I keep them open because, you know, one of them's my email, one of them's Piazza, 3 of them are Slack groups, a bunch of papers I'm reading, a bunch of papers I'm working on. I've got, you know, my Python documentation for working with sentiment analysis and stuff like that. I don't like closing them because I'm actively switching between them. But I don't want somebody to suddenly say, no, you can only have 10. I want to have as many as I want to be allowed. as I want. So I don't really like this idea of limiting the number of processes. By the way, each Chrome tab is its own process. So you could also do this thing called prefetching. So the idea is hide the latency, so hide the page faults. So predict when you're going to have a page fault, and then have one of the other cores of your CPU prefetch the page so the fault never happens. So this actually, some systems do this, by the way. They will actually, like in the latest Spark architectures, they actually dedicate, I think it's 2 cores are completely dedicated to tasks like this. One is, I think, dedicated to the OS, and the other one's dedicated to like prefetching stuff. That works. But you know, I've only got 16. I don't really want to give up one of my cores just so it can do prefetching. I want to use that for what I want to use it for. So you can hide latencies by prefetching and dedicating, a certain part of your CPU to that. But that's a hardware thing. We're not going to deal with that. What we want to do is just try to be smart about which pages we actually keep in physical memory. This is also known as Cache Eviction Strategies 101. So, simple page replacement. Let's use first in, first out. So the idea is that when physical memory is full, and you want to load in a new page, but there's no space for it, how do you choose who to evict? You want to evict somebody who you're probably not going to use in the near future. First in, first out is very fair, very easy to implement, does not perform so well in terms of reducing page faults. Now, these examples in the slides aren't necessarily the best. We'll go through it. So FIFO, we're always going to replace the oldest page in memory, so whoever was loaded first. So in our RAM, we're going to pretend we only have 3 frames. That way the example fits on the slides. And we're going to do a bunch of memory accesses in order. So first we start with nothing, because when you load the address space or load the program to start with, you're not going to load any part of the address space. So the first time we try to access something in the address space, it results in a fault. So we load A, we have space for A. Then we load B because we had space for B, but it was still a fault because it wasn't there. And then when we try to access C, it's a fault, but there was space. The first time we actually have to evict somebody is on memory access number 4. And that's where we want to access something on page D, but there's no space for D. So I'm going to choose the oldest of A, B, and C to evict. And I evict A, and I insert B, or D. Not too bad. Now, here's the problem. Right after evicting A, I end up using A again. So I kick out B, and then right after evicting B to insert A again, I use B. And so I evict C so I can insert B. So while this is very easy to implement, it's not necessarily good for minimizing the number of page faults we're going to get. And in fact, if you look at this, of these 12 memory accesses for this particular example, only 3 of them resulted in hits. So what is the optimal page replacement algorithm? How good would it do? So the optimal page replacement strategy, and we do know what it is to simply replace or evict the page that we are not going to use for the longest period of time in the future. So looking at these memory accesses, when I have to evict one to insert D, I look at A, B, and C, and I look at my memory accesses and I say, oh, I use A right away and I use B right away, but I don't use C until operation 10, so I'm going to evict C. So I evict C for D. Hit, hit, and then I have a miss. And then I have to choose between A, B, and D to evict. Well, I use A and B right away, and I don't use D until 11, so I evict D. Hit, hit, miss. Pretty good. So of those 12 operations, 5 of them ended up being hits. And this is as good as you can do. So if we know how to do this, why aren't we doing this? I don't know about you, but I don't know the future. Your computer doesn't either. So this is impossible because no computer knows the future. We don't know what the future memory accesses are going to be. We don't actually know. So this is impossible. Put a big X through it. But we can predict. It's not 100% accuracy, but we can predict. The first thing we note is that if you write a program, and so we have spatial and temporal locality. Spatial locality is this concept where your program does things in a sequential order. If you're accessing an array in a loop, you're accessing the array elements in sequential order. Those regions of code are either falling on the same page or a page right beside that page. So that's spatial locality. Programs are likely to access parts of memory that are really close to the parts of memory they're accessing right now. Temporal locality is the fact that pages you are accessing right now are very likely to be pages that you are accessing in the near future, especially if you're like looping through an array, right? 4 kilobytes per page means, you know, at least 500 of those memory accesses are going to be on the same page. We can take advantage of localities to try to minimize the page faults. Now again, the example in the notes is not that good because it's going to make it look like this is a terrible scheme. It's actually a lot better in practice, but this scheme is called least recently used. And with least recently used, we are going to evict the page that was least recently used to perform a translation. So when we have to insert D, A was least recently used, so we evict A. Now, unfortunately, that one didn't work out. Again, this isn't necessarily the greatest example. And we end up with some pretty bad faults because this is a pretty bad sequence of memory accesses. As I said, in practice, this would work out a lot better. But here's the problem. You can't implement this either. Well, it's not that you can't. It's just that it's complicated. So number one, your computer, your operating system, which would be performing these evictions, only knows about the page fault. It doesn't know about every successful address translation. So it doesn't know which page table entries were least recently and most recently used because it only keeps track of the faults and the TLB misses. It doesn't know about all of the hits. Now you might be like, well, couldn't we have, store a date or a timestamp every time we use a page table entry successfully? Let's put a timestamp into it. That's costly. Number one, it takes space. And number two, it's going to cost time to perform that update because you actually have to interact with the clock device to get the time, and then you'd have to write it down, and that's just too slow. So least recently used isn't practical either because the kernel only knows about unsuccessful translation. It doesn't know about the successful ones. So what are we going to do exactly? Scrolling the wrong way again. So what we're going to do is, since we don't want to store an actual timestamp, because a timestamp is quite big and it involves the clock, we are instead going to have a single bit keep track of the use of each page table entry. We're calling it the use bit. And the idea is that every time the MMU uses a page table entry to perform a translation, it sets the use bit to 1. And then periodically, the use bits will be read and cleared by the kernel. So it's not an accurate representation of when you were used last. But you can know that if the use bit is 1, it means you were used since the last time the kernel cleared you. So it's an approximation to least recently used. We know if your use bit is 0, you have not been used since the kernel cleared you last. So let's actually implement an algorithm with that strategy. And this is called the clock replacement algorithm. And I don't want to use this example on the slides here. I'm actually going to open up a program. And it's probably not going to work straight up. There's some kind of weird bug with the Wacom pens with this. Part of my pen fell on the floor again. Should really glue that back together. Oh, it's working today. Yay. So, yeah, it's not one note. Woohoo. See how it does. I've never really used this program before, for the record. I zoom in? Oh, there we go. Let's go page width. Here we go. Sorry, it's exciting not using OneNote. Even if this program's buggy, it's not OneNote, but it's still exciting. So here's what we have with the clock replacement algorithm. Instead of representing memory as just a rectangle, we're actually going to represent memory as a clock. And I'm going to horribly draw what looks like a pizza. And in the middle circle, this is the value of the use bit. So I'm going to have the use bit this. And then into these boxes up here, I will indicate the name of the page table entry that is stored in each of them. So this is our physical representation of RAM. So what we have for the clock algorithm is a victim pointer. And when we get a page fault, let's say I want to insert I. So I look, and we can see here that memory is full. So I have to choose somebody to evict. So I look at the use bit. And this is inside the kernel, and I see that the use bit for A is 1, which means since the last time it was cleared, it was used. So what I'm going to do is I'm going to reset the bit to 0. And then I'm going to advance the victim pointer to the next entry. And I see that its use bit is 1, which means it was also used recently. So I'm going to reset its bit to 0, and then I'm going to advance the victim pointer. And now I see one where, hey, the use bit is 0. This is the perfect victim. So I am now going to, oh, that's a highlighter. I want an eraser. So I am now going to insert my entry here. So I'm going to put I in. And I'm not going to set the use bit because after inserting I and updating the TLB, the address translation will happen again, except this time it will succeed, and the MMU will then set this use bit to 1. We don't want in the kernel to set the use bit to 1. We want the MMU to perform that operation for us. So we're just going to MMU to that. And then before I do that, of course, since I know I just inserted this one, I'm going to advance the victim pointer once more after successful insertion. That way I know the next time there's a page fault, I'm not going to be trying to victimize the one I just put in. Okay. So that is how the clock algorithm works. And we're going to keep going around and around and around the clock. Now what's interesting is what happens if you're in a situation where every single use bit is 1. So let's say my use bits are all 1s. 1, 1, 1, 1. If all of the use bits are 1, people might be thinking that, oh, that means that you're going to just cycle around and around and around and around. But you won't. Because what happens is as you check each of these use bits, you reset it to 0. And so once you reach the first one you tried to victimize, it will now be a 0, and so that's the one that you will turn into the victim. So this is guaranteed to stop. And this is a way that we can use the use bit, which estimates how often or how recently something was used. This is how we can use that technique to perform our cache evictions. That's pretty cool, right? I think it's pretty cool. All right. So that is the end of our virtual memory section. It's all done. And what I'd like to talk about is our next episode. So in our next episode, we are actually going to start a new topic, which is scheduling. And for those of you who have noticed, don't forget we have reading assignments. And I think those reading assignments should become available to you really soon. The papers for the reading assignments are posted on Piazza already. So you should be able to do that. And then, Sorry, I can't log into Learn because I need to use the Duo key, and I don't have my cell phone sitting here, so I can't log in. Anyways, the reading question assignments should be made available to you soon. The first reading assignment is actually a scheduling reading assignment. So, and it's based on a schedule known as the Lottery Scheduler. And we will start talking about scheduling in Thursday's episode. And then after scheduling, we are going to start talking about devices and I/O, which is another favorite topic. And then after devices and I/O, it's file systems and then virtual machines. So that's kind of the layout for the rest of the term. And of course, we'll talk about assignment 3 when it is appropriate. So I hope you have a good afternoon. And if you noticed any audio-video issues, please let me know by email or over Piazza so that I can make appropriate adjustments before the next episode. But other than that, we will see you on Thursday.